Bounds are going to help us reduce the amount of work we have to do when dealing with our rational zeros theorem. A polynomial is said to have an upper bound when there are no zeros that are greater than that number, and it's said to have a lower bound when it has no zeros that are less than that number. So for a quick example, let's say we have a polynomial function with the zeros minus 5, minus 3, minus 1, 2, 6, and 8. The greatest zero is 8, so this is the upper bound. Because this function would not have any zeros greater than 8. And this right here would be the lower bound. Because the function would have no zeros less than minus 5. So that's what bounds are. An upper bound is the greatest x0, and the lower bound is the smallest zero of a polynomial function. So now that we know what bounds are, let's talk about the rules for bounds. And the rules for bounds are as follows. Let f of x be a polynomial function with real coefficients and a positive leading coefficient. Suppose f of x, so suppose our polynomial, is synthetically divided by x minus k. Then, if k is greater than 0, and each number in the last row, when we've done our synthetic division, is either a positive or a 0. So once we've done our synthetic division, the bottom row, if everything is a positive number or a 0, then k is considered to be an upper bound of the zeros of f of x. So if we get the positives and the zeros in the bottom row, when we do a synthetic division of k is greater than 0, then that means that that 0 is the upper bound, so it's the greatest possible 0 of that function. And similarly, if k is less than 0, and the numbers in the last row are alternating in sign, then k is the lower bound of the zeros of f of x. So it's sort of the same idea, but instead if we have some k that's less than 0 and we do synthetic division, and in our final row we get alternating signs, instead of it being an upper bound, it's a lower bound, so that means we have no 0 that is less than whatever k is. And there is one more note, and that is if a 0 appears in the last row. So if we have a 0 that appears in the last row when we've done our synthetic division, that 0 may be given a positive or negative sign. So let's do a few examples, I guess, to talk about these rules, to kind of explain these rules. So let's say we have a positive k, and I do some synthetic division and I get 1, 2, 3, 4, and some 0. And I want to know if this is an upper bound. So if we want to know if this is an upper bound, we do some synthetic division of some number, some stuff. Doesn't matter what it is. All that matters is what's on the bottom. You can see that this is a positive number, this is a positive number, this is a positive number, and this is a positive number. And we have a remainder of 0, so we know that it's a factor. When everything is positive on the bottom, that means it's an upper bound. According to our first rule up here, if we have a k greater than 0 and each number in the last row is either a 0 or a positive number, that means k is an upper bound of the zeros of that function. So that means that whatever k is, it's the highest 0 of x. There is no, so let's say k is equal to 10. That means there would be no 0 greater than 10. That means we couldn't have a 0 of 11 or 12 or 13. None of these are possible because k equal to 10 is the upper bound. And if we had some situation where we had done synthetic division, we got 1, 0, 3, and 4. We have a positive, we have a 0, we have a positive, and we have a positive. And we want to know if this is an upper bound or not. This is still an upper bound because the 0 can be a positive or a minus, and in this case we're going to choose for it to be a positive. And it's an upper bound. We'll have one more situation with a positive k. If we have a positive k, we do synthetic division, we get 1, let's say minus 1, 3, and 4. We have a positive, a minus, a positive, and a positive. So this is not all positive, and this is not a 0, so it cannot be all positive. So this is not a bound, not a upper bound. This is still a 0, but it's just not an upper bound. We can have zeros that are not upper bounds. There's only going to be one upper bound, there's only going to be one lower bound. Everything else is just a plain 0. So in this case, k is just some 0, and it's not an upper or lower bound. So let's talk about some minus k possibilities now. So if we do synthetic division and we get 1, minus 2, 3, and minus 4, when k is less than 0. So in this case we have a positive, a minus, a positive, and a minus. So that means that k is a lower bound, because the signs are alternating. And if we had a situation where we got 1, 0, 3, minus 4, and a 0 remainder. Here we have a positive, a 0, a positive, and a minus. But this 0 can be either positive or minus. So in this case we're going to choose for it to be a minus, in which case k would still be a lower bound. So now that we understand what the bounds are and how the rules work, let's do an example and see how bounds might be able to help us eliminate some of the work we might have to do when looking for the rational zeros of a function. So here I have an equation, and I want to know what the rational zeros are. I want to know what the rational zeros are. So the first thing I'm going to do is I'm going to use Descartes' rule of signs to figure out how many positive zeros I have and how many negative zeros I have. So here we have a positive, a minus, a minus, a minus, and a minus. We can see that there's only one variation in sign. So that means we're going to have only one positive 0. And we can look over here and see that this is an x to the 4th. And the maximum amount of positive zeros there can be is 1. So that means there can be a maximum of 3 negative zeros, and we have to include the differences of positive integers. We have to keep subtracting that series of 2's. So that means we can have 3 or 1. And if you don't like doing it this way, you can always put in f of minus x for everything over here, and then count the variation in signs. But I'm not going to do that, because that just takes up time. And this is not about the rule of signs. So we found out that there is going to be there's going to be one positive 0 and either 3 or 1 negative zeros. So now that we know how many zeros there can be for the positive and minuses, let's figure out what the pool of possibilities are. So we have a 6 and a 1. So we need to use our P over Q, where P is the factors of the constant, and Q is the factors of the leading coefficient. And the constant in this case is 6, so the factors of the constant are plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6. And the factors of the leading coefficient are 1. So we have to divide everything. So we have to know what all the possibilities are. So that's going to be plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6, divided in turn by plus and minus 1. So we have to know all the possibilities. And thankfully, since it's just a 1, it's going to be very simple. So our possible zeros are plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6. So now that we have all of our zeros, let's think about what this is going to mean for the bounds. Since we only have one positive zero, whatever the positive is going to be, it's going to have to be the upper bound, because it's the only positive number. So it's therefore going to be the upper bound. So whenever we find our positive zero, it's going to have all positives and zeros in the bottom. But in this case, the bounds aren't very helpful. I just wanted to just bring that up, I guess. Whatever that zero is going to be, it's going to have positives and zeros in the bottom. For the minuses, it can help us eliminate work. Because if we find, let's say we start testing for our negative zeros, and let's say we find out that minus 1 is the lower bound. That would mean that there is only one zero, not 3, because minus 2 couldn't be possible, minus 3 couldn't be possible, minus 6 couldn't be possible. So that's a way that it could eliminate work for us. So when dealing, if you plan on using bounds, you're going to want to pick carefully where you start. Because if we start at minus 6 and we find out it's not a bound, then we potentially are doing extra work. Because if we find out that 2 is the lower bound, then we can eliminate minus 3 and minus 6. If we find out minus 3 is the lower bound, then we can at least eliminate minus 6. If we find out that minus 6 is the lower bound, then we couldn't eliminate any of the work anyways. So it doesn't make any sense at all to start with minus 6, because if minus 6 is the lower bound, then we're going to have to test for all of these points anyways. So it would make sense for us to start either in the middle or on the left side when testing for the minuses, because if one of these is a minus, then we can eliminate some of the work. But if minus 6 is the lower bound, then we can't eliminate any of the work anyways. So when you're planning on using bounds, it makes sense to pick carefully where you're going to begin testing, because potentially you'll be able to eliminate a lot of work. And if we start at minus 6, then the bounds aren't going to be helpful to us really, because that's the only thing the bounds are really useful for us for. It's just to eliminate work. So let's start with the positives, and I'll start from 1 and I'll go to 6. So we have 1, we had 1, minus 1, minus 5, minus 1, and minus 6. So 1 times 1 is 1, we get 0, 0, minus 5, minus 5, minus 6, minus 6, and we get minus 12. So this is not a factor. Next we'll go on to 2. So bring down 1, we get 2, positive 1, positive 2, minus 3, negative 6, negative 7, negative 14, and we get negative 20, so 2 is not a factor. Now we move on to 3. So this gives us positive 3, positive 2, positive 6, positive 1, positive 3, positive 2, positive 6, and we get a 0. So we know that 3 is a factor. Now let's check to see if it's an upper bound. We already know it's an upper bound because we only have one positive 0 according to Descartes' rule of signs. But let's double check. 1 is positive, 2 is positive, 1 is positive, 2 is positive. So 3 is an upper bound. Now let's begin with our minus. So like I said earlier, it's best to think a little bit before starting to test points when dealing with bounds. If we only had, let's say, plus and minus 1 and plus and minus 2, we have such few numbers that it doesn't really make sense for us to use bounds. But here we have quite a few numbers, and the bounds can potentially eliminate some work. Since we can have 3 or 1, I'm going to start in the middle somewhere. I'm going to start with either 2 or 3. So as if we get 2 or 3 is a lower bound. If we get 2 as a lower bound, then we can eliminate minus 3 and minus 6. If we get 3 is a lower bound, we can eliminate 6. If we test 1 and we get it's a lower bound, then we can eliminate all 3 of these. But I'm going to start with, I'll just start with minus 2. In case 1 is a lower bound, it eliminates all of our fun. So minus 2, we have 1 minus 1 minus 5 minus 1 minus 6. I could have just used this over here, but whatever. I already wrote it out. So 1 minus 2 minus 3 positive 6, 1 minus 2 minus 3 positive 6 and 0. So minus 2 is a factor, but let's see if it's a lower bound. We have a positive, we have a minus, we have a positive, we have a minus. So these are alternating signs, therefore x is equal to negative 2 is a lower bound. So we go back up here, and what we said earlier is that we could have 3 or 1. Actually, let's go over here first. So we said that 2 plus or minus 2, where's my scroll? Oh, there we go. So we said plus or minus 2 is the lower bound. So this is the lower bound. So that means it can't be minus 3 and it can't be minus 6. And we had a possibility of 3 or 1 zeros. So all we're left with is minus 1 being a possible 0. But we must have 3 or 1. So therefore minus 1 cannot be a 0 either, because we don't have a third 0. Let's say if minus 1 was a 0, we'd have to have another negative number that is greater than minus 2 in order for this to be true. So we already know that minus 1 is not a 0. So therefore we've eliminated a whole bunch of work. We only had to test 1 point. We got lucky. We got minus 2 was the lower bound, and therefore we were able to eliminate these. We weren't able to eliminate 1 based on lower bound, but the lower bound in conjunction with Descartes' rule of signs saying that there's 3 or 1 eliminated minus 1 because there is not a third possible 0. So we didn't have to test for minus 1. We know that it's impossible. So we get that the zeros are, let's change the color. So our zeros were x is minus 2 and 3.